Hello, welcome back, guys. Um, okay, to trying to do this practice on Kaggle under deep learning. It's practice, I think number five, I think, or number six. It's about data augmentation. Data augmentation. So in deep learning, we're talking about image classification, for example, right? And is using, for example, convolutional neural network. When you put, let's say you have hundred of training images, right? Let's say you want to identify, for example, cat or dog or cat, hot dog or not hot dog, right? So you have these hundred training images, right? Different kind of cats, for example, or and different kind of dogs, right? So let's say 50-50. And you feed forward it to the neural network. And for each of those image, because you want to be more, so basically if you I don't know if you reach to this point. The way I see it, deep learning is about curve fitting. So you have like linear curve, which is like a straight line, right? Straight line, and then you have let's say a quadratic curve, which is like a kind of like a U shape, and then you have a curve that has exponential to the power of three, which is more like more um, kind of more complex the shape, right? So deep learning is about is basically a very complex nonlinear functions, right? And why nonlinear? Because on every layer, so if you look at the architecture of the neural network, right? There's the first layer, which is the input. You're taking all the images, let's say 100 images, and then there's the second layer. We call it, let's say, and then there's third layer, which is the output. The third layer is basically it will classify is a dog or not a dog, cat or not a cat, right? This is just very simple layers, just three layers, right? The input, the output, and the one in the middle, right? So the one in the middle is called it's called the deep. Basically, it's like hidden, kind of hidden input, right? So when you feed forward the image, let's say a cat, the idea of data augmentation is to want to make it because basically deep learning is about curve fitting. Yeah? It's basically to extract all of the information is and then to get like what is the most important features for that particular if it's a cat or if it's a dog or if it's a hot dog to make it to make the what do you call this to make the the network more robust or the classifier we call it the classifier more robust. More robust means it doesn't get fooled easily. For example, if you put an input an image of cat and the cat is like in the middle, right? And then it identify it's a cat. Oh, it's good, a cat on the third layer. Boom, a cat, perfect. But if you move it a little bit to the left or to the right, the image of the cat on that frame, or to the to the diagonally to the left or diagonally to the right, and then it doesn't work. So that means it's not robust, right? It's or in deep learning, what it's also called overfitting, right? So it's only works for a very specific sample, so it's just overfits. It doesn't generalize really well, right? So we want to minimize that overfits. We want to make it more generalized. So we introduce data augmentation. So you can basically move kind of the object that you're trying to classify around the frame, right? If you have like 64 by 64 pixels and the object is, for example, I don't know, it's just occupying, like say, 20 by 20 or 20 by 30 or 30 by 30. So you want to still move it around, you know, so make it more flexible. Or you can like flip it. But you can do that as at some example. For example, if you want to identify urban space or a city or not a city, you can kind of like flip it because the image of the city, when you think about it, if you flip it, probably it still looks like a city, right? The same thing probably like and it works in the real world too, right? Uh, the same thing as, for example, if you want to flip a person like standing over here, standing to the left, or standing to the right, you can flip it. But it doesn't make sense if it's like you flip it up and down, right? Because in the real world, it doesn't work like that, right? The same thing for example, for probably I think, yeah, I don't know, animal or cat, or even like you cannot just flip it to the left to the right. I think it doesn't make sense, kind of. Um, yeah, but probably for objects, a non-living object, it still makes sense. So it depends on the the problems that you're trying to solve. Um, Definitely data augmentation, I think it will help to generalize better the network, but you have to think of how do you want to augment it, right? Because there's many parameters. In this case, you will see like you can like augment it, like you can flip it, you can move it to the left, to the left, to the right, you can push it up and down, yeah, and so on and so forth. Okay, so all right, over here. Okay, this is just gonna take probably like 10, 15 minutes. We're gonna try to just run this code. So I'm just gonna try to brief through, like explain what each of the codes like means. I don't really understand all of them, but I kind of understand like um, more or less. Hey, but I'm also learning like you guys, so the best way to teach yourself is to to learn anything is to teach it, because when you learn, right, you are when you're teaching, you are actually creating a pathway in your brain, and then you're saying like this, what I'm saying right now, what the words is basically what I'm saying is creating also a pathway in my brain. So and that's part of the learning process. Okay, so the first let's see if I can make it bigger here. Okay, this one from TensorFlow Python cross application import ResNet 50. So ResNet 50 is the pre-trained model, right, from the world of convolutional neural network, right? Sequential, I think, is a type of deep neural network that is like in sequence. I think that's my understanding. I could be wrong. Uh, Dense here, it's so you see there's a lot of neurons, right, in each of the layers. I think dense means every neurons like are connected to one another. So if you look at, for example, the second layer, right, the intermediate layer, so the first, like say, and there's like, for example, there are three neurons. Each of those neurons are connected to every input. So if you have, for example, let's say you take 64 by 64 images. I don't know what is that, 64 by 64. I think like 12,000, is it? 60 times 60? Yeah, it's about, no, it's about 1,200 something, right? So there's 1,200, let's, for example, inputs, right? On the first layer, which is basically all the pixels, yeah, from the 64 by 64 pixel, and each of those will be connected to the neuron on which is on the next layer. So that's, I think that's what dense is. Flatten, I'm not sure. Let's see what flatten means. Import set TensorFlow flatten. Let's see. Shallow structure shape. La 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 la. La 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 la. La 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 la. I do not know what is flatten. Give me some answer. What is flatten? Flatten beds in TensorFlow. Um, the best way to flatten a 2D tensor containing factors in TensorFlow. Oh, I think what it means is to make it just like what the word says. Um, let me see. Flatten do. I'm so sorry, guys. This takes longer than what I'm thinking. So we'll go to Stack Overflow. Just be patient. Uh-huh. Do, 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 do. I don't really know what the flatten is. Hmm. Okay. Okay, last chance, okay? Otherwise we have to just go through this. TensorFlow flatten versus NumPy flatten. Effect on machine. Okay, in I'm starting with deep learning using Keras and Network. At first I'm stuck with the DAO that uses flattening an image could be. How is it different from using flatten function? Or does the effect on training? What does flattening an image means? I have no idea. Just to make it all in one factor, like the biggest difference between NP and TF layer is that NumPy operation applicable only to the static ND arrays, while the operators can work with dynamic tensor. For the say overhead and returns on and use any of the flat operation operator. Okay, if that is already a tensor. Uh, use TF Krasler inside model if this operation is needed for some reason. Yes. Model proper backpropagation. Models are. There will be proper connection when you connected into input output. You don't intend to create a network. Don't use a TF layer. When you use it get added operation, it can operate on tensor. Okay, you directly run, blah blah blah. The flatten function in NumPy does a complete array flattening, meaning that you end up with a single axis of data. Okay, one dimension. Oh, okay. Single axis of data, one dimension. So you end up with 1D array of 20 elements. Okay. In TensorFlow, the flatten layer preserve the batch axis. In the previous example with TensorFlow, you would still have a shape of 5,4. Yep. Okay. I give up. I don't know. Uh, it's just saying it flattens the the data or the tensor, but I still do not know what it means to flatten. I just to make it like the operation like easier, which is necessary to function in a neural network. I don't know. Global average pooling. This is I think has to do with max pooling. So after the image is already computed on the neuron, right? So you apply the WX plus P, and then you do a non-linear activation, let's say ReLU or 10H, and then you feed forward it to the next layer. I think the max pooling, I might be wrong. It's where at the end, and probably also in the last layer, you would get, like, for example, uh, it's more like a convolution in a way that you create kind of like a filter. For example, you have four image pixels, let's say, right? Four pixels, and then you get out of those four. If it's max pool, you get only the maximum. Just means to extract the maximum out of the four. So that's for max pooling. And then this one, it says a global. Global means I think it takes the whole thing in two-dimensional. I think on is on average. So probably it will, if it's like all the in two dimension, there's, for example, there's like 64 by 64 um, tensor. So it will take the whole thing 64 64 by, because it's global. And then it will take the average of that. It will compute the average for that, and then it will extract that average, and then we'll take that as an output. Okay, so but max pooling or average pooling, it's the use case is basically to squeeze out what is the most kind of important factors. Uh, um, it's a way to reduce a lot of dimension into like one dimension. If you have four dimension into one dimension, if you can reduce what is the most important thing, like to prioritize just to get that thing. So it's another way to extract a kind of like the most important features from the network, from the whatever you're trying to analyze, to classify. Okay, num classes. So there are two classes, right? In this case, we are trying to, I think, detect. I don't know what you're trying to detect here. Hmm. Yeah. I think it's uh what is the image? Oh, it's a rural urban photo here. Rural and urban photo over here. So that's what we're trying to. That's the number of classes, right? And this is the just giving a direction where to go for the weight, right? The pre-trained weight, right? Remember, is a ResNet 50 is a pre-trained model, so it has all of those parameters already set, which is the weights and the biases. Um, so this is creating a new model, which is sequential, right? Sequential means again, like what I just mentioned, it's just kind of in sequence. It's not, I think it's not as compared to the recurrent neural network. One neuron can go back to the neurons to the neuron itself. It doesn't have to go feed forward, or it doesn't have to go. It can even go back. I think go back to the previous neuron. So I think sequential is more like in sequence and more like keep on going forward in terms of the neural network. My new model add, so you add the pre-trained model, and then you include all of the parameters. You want the pooling to be average, include top. It's false, meaning you take out the top, the last layer, right? Because you're just using a pre-trained model, so you are, they call it a transfer learning, right? And then the weights is using ResNet weight path, right? Which is this one, right? That's the weight, all of the beautiful weights and the biases. It could be like thousand millions of parameters. Uh, and then my new model dot add, I think that's why they call it hyperparameter. I don't know. It's dense. Again, dense is just one neuron will be connected to every neurons before that. So it's very dense, very like integrate all of the connections there, right? Um, Number of classes, two, and the activation we are using Softmax here. So there's a different kind of activation function. ReLU, I think, is the most common one, and I think it's the most common and the most kind of effective. That's what I heard. ReLU, right? That there's 10H, but I heard many people doesn't use 10H anymore. Um, but activation is basically all of the activation function. They are non-linear. That's very important. Okay, non-linear, and that is the key to make, I think, deep neural network works. Because without that non-linear function, the function itself is all linear. Because remember, neuron basically is wx plus b. That's all. That's it. That's the neurons. And wx plus b is a linear function. So linear means it's a straight line, right? The output is proportional to the input. It's always proportional. So it's always a straight line. If you put, let's say, an input of 50, the output would be, let's say, affected by 20, right? Which means if it's linear, if you put another 50, then the output would be affected by 40 because it's linear. It's a line, right? And without activation function, deep neural network wouldn't work because it's going to be just too rigid. It's going to be too, uh, yeah, overfit. You can say it overfit, right? Because it's just going to be a straight line. So the activation function is kind of the key, and it's non-linear. So if you have something linear and then you put at the output is non-linear, then everything becomes non-linear. So that's kind of like the magic. So when you think about it, it makes sense, right? So softmax is a kind of a nonlinear function, and softmax is basically, by intuition, is taking soft and max. So it's pulling. If you have a number, for example, um, how do you say it? Between let's say there are four numbers. Let's say one 120 uh, 121 and 80. Softmax, the function, if we put these four numbers into the softmax algorithm, it will basically, the softmax function will take out the maximum number, which is 100. It will pull it out, and then it will depress all the soft. The soft means the low number. So let's say 1 and then 20, it will like make it like so, make it really like low. So if you look at the output of the softmax function, is an exaggeration of the whatever the maximum number in that group. So it's kind of also like a feature extraction to know which one is the like the saying the richer get richer and the poor get poor. It's kind of like this, the softmax function, when you think about it like that. It's like basically it's like a softmax function. So the maximum number in that group will be being pulled and then being like more outstanding because you can see it clearly. Whoa, that guy is so tall, right? And then the rest just like being like repressed. So that's what the softmax is. Um, say no. Okay, next one. Say no to train first layer. Okay, yeah. So my new model dot layers 0 dot trainable false. Okay, so because you don't want to train the first layer. My question is, how many layers are there? See, because the last layer is that's the one is being retrained, right? That's for sure. I think layer 0 is anything probably. Say no, not to train first layer. Okay, so but I think layer 0 just refers to anything that doesn't include the top. So for example, if you have like 3 layers or even 4 layers, you say false include top, so you don't the top is false means you exclude the top because you want to replace it with a new top with a new layer because you want to train this. But whatever remainders, so the layers behind that top, which is if it's a 4 layers, the layer number 3, number 2, number 1 will be preserved because you don't want to train this because this layer over here, the one at the in the beginning, it's already pre-trained and you don't want to train that because you want to save money and time, right? And headache, right? Because somebody else already done it and it's already good. It's already kind of almost perfect, and right, you don't want to mess up with that. You just want to mess up with the last layer, right? So you want to put the layer 0 dot trainable false because it's not trainable, it's fixed. You don't want to mess with this, like the last layer, right? The layer 0, the last layers without the top, because you want to save it, preserve it in a museum. It's a relic, right? You don't want to touch. That's it. Full stop. No question asked. All right. Okay. So the next one, my new model dot compile. Okay, now it's compiling already. Compile means you are trying to determine what are the compilation model to compile. To compile means to 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 optimize, to do back propagation. So that this first my model dot add, that's just to determine the kind of the what are you doing in terms of the overall architecture of the neural network, but you haven't defined yet the so you need, because in a neural network you have an image, right? All right, and then you want to train it, right? Train the image, right? To identify, in this case, an urban or city or urban, for example, right? And once, let's say, one image, right? And then you compute the result, you compute the output, and you want to know whether the output is good or not. So you want to compare it with the predicted, sorry, with the label, right? And then because of that, you kind of know the error, right? Remember the error, right? And then you want to compute the loss. You want to minimize this error, and in order to minimize this error, you have to optimize. They call it, and then it uses the back propagation algorithm, right? In a deep learning. So compile is that whole process when you compute the error and the loss function, and then you want to back propagate to the network. How to minimize, right? With gradient descent, with and back propagation is it's the whole algorithm. Gradient descent is inside of it. It's kind of, probably if you're new to this, it's kind of confusing, but just take it as it is. The compile function, the dot compile here, basically it tells the computer what method to minimize the error, right? Because you have to minimize the error and to adjust the parameters. That's right. Okay, I forgot about it. That's very important. To minimize the error and to adjust the parameters, right? So when you train the network, you want it to be more and more accurate, right? You don't want to train the network and then it's going to be less and less accurate, and that defeats the purpose, right? So you want to minimize the error, right? So in terms of minimizing the error, that's called a dot optimizer. Um, so the uh, the parameters that we need to set here, it says optimizer equals to SGD. I think SGD stands for stochastic gradient descent. It's just a type of back propagation algorithm, a specific type of back propagation algorithm. Back propagation algorithm is basically to find tune the parameters, to tweak the parameters in order to minimize the error. That's okay. So, and this is one of the most common um, backpropagation algorithms, stochastic gradient descent. And then the other algorithm, I think, optimizer is called gradient descent, right? I think there's several of them. And then for the loss, you want to use is using categorical cross entropy. I'm not sure what's the detail about this, right? Matrix, the matrix that you want to take out or as an output is the accuracy instead of probably, or you can put probably there's a loss to accuracy, right? Okay, so whew, that's explaining just that what 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 line of codes. Okay, we're gonna run this now. Boom. Uh, running, 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 still running. Okay, done. Okay, so if you want to know, for example, let me see. Um, okay, now we're into the data augmentation. Okay, so this whole paragraph is just about setting up the model of the architecture and the model and all of the like which layer to train, which one we keep it as is. We also determine what are the um, how to minimize the error, how to tweak the parameters in order to minimize the error. So this is basically what the whole paragraph is all about. Okay. Okay. The next paragraph is about fitting that model because you already created the model on the first paragraph, right? For the feed forward and the back propagation and propagation too. And then now we want to fit the model with data augmentation, right? Um, Not just so with the original data plus the data augmentation. So here it goes. So from TensorFlow, Python class application RSL 50 import pre-processed input so it's just importing a specific function. It's called pre-processed input. Basically, as the name suggests, is to pre-process the input before you can even input it into the network, right? We'll see how it goes here. Okay. Um, and then this one free TensorFlow image import image data generator. Okay. So from the image, we're importing image data generator. Okay. We'll see how it works. Image size is 224 pixel. Why? I'm not sure why. We'll just take it as is first. So now we are generating a data generator with augmentation. Okay. So we use the image data generator function, the one that's already import, and then we put all of these parameters inside, right? So the pre-processing input function equals pre-process input um, horizontal flip. So you are going to flip it horizontally, basically. So if you have a city, a picture of a city, you flip it horizontally, like that, right? Vertically means you upside down like that, right? So you kind of like it's like you're looking the city through a mirror, kind of, right? Which just makes sense, right? In the real world, it still kind of makes sense, but it doesn't make sense, for example, for probably for I don't know, for probably for a person, it doesn't make sense to flip it um, horizontally. I don't know, could be, but not definitely not vertically, because then people will get upside down, right? Unless we're living on a like inside a planet or whatever, right? There's no gravity, right? But that's another topic. So with shift range, so you're shifting the range about 20%, 0.2. So the width of the um, I think this one is shifting the width 20% left and right, randomly. Yeah, randomly. I'm not sure whether that's shifting left, right, the width, or just like shrinking it. I don't think it's shrinking it. I think it's more just like, shifting it to the left 20 by 20%, shifting it to the right by 20% randomly, right? And then the height shift range is also 20% up and 20% down, like that, right? So imagine if you're taking a photo of a city, you are you're looking at the viewfinder of the camera, and then you're just like going up by 20%, going down by 20%. So that's what does it does basically. But this one is not doing like constantly, but it's doing it randomly. So it's not every pictures go through this. It's just take the pictures whatever go through the network, go through this um, a function, and will do it randomly. Okay, so we already generate the data with augmentation, and now we want to use that uh, as a trend generator, right? We want to use it as a trend generator. So uh, equals data generator dot flow from directory, right? Okay, so this is just telling uh, where can you get all of the training data, right? So you can randomly augment those, right? Um, the target size is the image size, so it's 224 by 224. The batch size is 24. I think so. Every 24, so that's like the batch. So every 24 image, it will look through 24 images, and then we'll choose randomly, blah 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 blah, right? And then augment some of that, and then we'll get another second batch, 24 images of the second batch, look through randomly, and then get some of this augment the pictures, and so on, right? Until it's all done. Class mode is categorical. I'm not sure about that. Okay, well, we'll skip that. Okay, and then we also want to data generator with no augmentation, right? Because um, that's kind of obvious, right? Because when you want to train the network, you want to train with the real image, with the real data, plus the augment, right? To make it uh, more generalized, so it doesn't overfit, right? So you do the same thing. Data generator, no augment. It's from image data generator, pre-processing function, pre-process input, and then you do the validation generator. Okay. Okay. So we, it seems to me they are putting the real data as a validation data. So they use that after the training is done, right? So data generator now from the same thing, categorical. Okay. So now it's trying to train the model, right? So we are doing this basically. My new model, my new model is basically your model, which already defined on the first paragraph, painstakingly what are the feed forward, like which whether it's using transfer learning, which one is to leave it as is, which one is to take away, which layer to take away, what kind of like back propagation or loss function algorithm to use, right? So that's what my new model is, right? Um, and then you want to fit generator, right? Fit generator and with these parameters. So you put the train generator, and remember the train generator is basically now it's a bunch of data that consists of the original image plus the augmentation image, right? Yeah, okay. And then step per epoch 3, I'm not sure about this. The epoch 2. So epoch 2 is basically it's the number of time every image goes through the network. So epoch 2 means there is 2 times. It's not just 1 time. So let's say if there's 100 images, this is combine all the raw, sorry, the original or the raw plus the augmentation goes through the training process all of 1 time, all of the address, and then it's gonna be repeat. The reason you want to repeat this because remember when you augment the data, it will augment randomly, right? Which means on the second epoch, right? When when it gets the data from the train generator, it will get a kind of different kind of data, not exactly different. Some of it, of course, the I think the raw, some of it probably like 90%, 80% are kind of the same, but probably like 20%, I'm not sure, right? Depending on because it's random, right? The augmentation is random, right? Um, so the idea also is to make it more again, I think to make it more generalize the curve fitting the model that you the classifier, right? So it doesn't overfit basically. So you want to put two. Um, you can experiment. You can put three, four, five. Yeah. But this one too. Remember, competition is costly. But again, hey, this is free, so you can like experiment all you want, right? And see which one is good. And I think my intuition is once you get like the best one, it could be like epoch number 2 or epoch number. Probably you should get the best one. I'm not sure about that actually. It could be the best one would have like it will be overfitting when you put like a validation data. The error will be like big. I'm not sure. Right. In general, you want the accuracy to be high during the training. Let's say like 98%, 90%, 99%, and also during the validation, which using the um, a completely new data. Ideally, so it's not the same data as the training. It will also give you more or less high accuracy with also a low error. That means the data you can like more or less sure that the model that you are been working on is good for 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 general data. It's not just for your kind of data, right? Because that's one of the main thing about deep learning, machine learning. You don't want your model to be biased, right? You don't want your model to be just good with your data, but once you deploy it in the outside world, it fails. It's fragile. It doesn't work. It's like fails to classify. For example, if you deploy it on the outside world to detect city or not city, you change a little bit of the, for example, the grass become like blue, for example, it will detect not city. But actually everything is the same. It's just the grass or probably is a fall color season let's say in here in the US is changing color. The three colors becomes like red, all red, the leaves. Yeah, everything is the same, right? With probably a little bit of snow, and then your model doesn't detect that, right? Or our model doesn't detect that. Then there's going to be a complete failure. We try to avoid that, and try to avoid it. We're using a lot of different like this thing, right? A lot of different like tweaks here and there, right? Um, and this is I think the hard part to become a data a deep learning a practitioner or a researcher is to know which one is the one that you tweak because there's so many parameters to tweak just to make it like um, more generalized, right? So that's I think where the intuition you have to kind of like practice, you know, a lot to know like which parameter is kind of, and I think depending on the context of the data, the problem is you're trying to solve, right? But that's the idea. You want your model to be anti-fragile, to be generalized enough, right? To be not easily fooled, right? So if somebody's trying to fool your model in the outside world, yeah, they will fail. Um, Okay, so epoch, okay, 2 steps per epoch. 3, I'm not sure about this. What does it mean step per epoch? I don't know what step is this referring to. Because it's trying to fit the train, and then one epoch, for example, the first epoch, and say 100 images goes through, boom, and then there are 3 steps. What are the steps? I don't know what steps is it. Yeah, I don't know. So the validation data is equals to validation generator. Okay. And then the validation steps is 1. Okay, so this one is trying to validate too. Okay. Okay. Got it. Okay, let's run this. Boom. Okay, found 72 images belonging to 2 classes. Found 20 belonging to 2 classes. Okay, so the epoch 1, it's what's this? It's second, and the loss is 0.79. The accuracy is only 61%. So it's quite low, right? And it's a high loss. The validation loss is 73%. Okay, so the validation actually is better, but the accuracy is about the same, right? For epoch 2, it seems to be better. The loss is significantly reduced, 42. The accuracy is like way up, like 76 is about like 16 point higher. Yeah, including the loss too. And the validation it's also higher, the validation loss. And the validation accuracy is 70%. Huh. So it's lower. Yeah. I forgot which defines overfitting. If the validation is higher, accuracy is higher than the training accuracy. Um, in this case, the validation accuracy is lower. I think that's the definition of overfit. Because during the training, you have a high accuracy, but validation is like you're deploying in the real world is actually lower, which means your model is not very good. You can say it's overfit or underfit. I don't know. I'm still confused within those two. I think it's overfit. Overfit. Because overfit, imagine if the curve is like this, and then you have your data points is just it's not it's not on the curve. Um, um, yeah. Anyway, okay. Let's try for epoch 3. Okay, so you can see here the validation loss is sorry, validation accuracy for the highest, okay, among the 2 epoch is 76, right? That's the best. And then that's during the training, and the validation is 70%, right? Let's do for epoch, let's say 5, 5 epoch. Hmm. Oh wow, oh wow. Why so high right now? I don't get this. Look at this. It's like 93%, 95, 94, 98, 97. Oh wow, that's crazy to jump. I don't know why why the difference is a lot like that. And this is 90%, all of them for the validation, which is pretty good. But all of the validation is lower than the training, the accuracy. Okay, let's do one more time. Okay, I just want to see how does this behave. It's still 95. Hmm. Oh wow. This is like 100%? That's crazy. How can it be? 100% accuracy. Epoch number three. Okay. Let's go back to two. So that's like an outliers. The first time it was like only 60%, right? You see that? Right now is like 98% always, like 90% and up. I already repeated like probably like 4, 5 times. Yeah, 4 or 5 times. Okay, I'll repeat one more time. Okay, and then we're done. Let's say epoch 3 right now. Oh wow. Really? 100%? Oh wow. Hmm, that's interesting. Is it because like I don't know. Is it because the model is already like being pre-trained? I have to like go back to the beginning. Let me go back to the beginning, okay? Let me go back here. I got an intuition because uh, I have to repeat this to reset the whole thing, probably to reset the model. Let's see. But it shouldn't. Hmm, I don't know because we are talking about just training the last layer, right? Okay, let's see. Let's see if it's low. Oh yeah, it's low. It's also like 60%. See that? Like 69%. Okay. Huh. This is interesting. If I do this again, it's going to be higher. It's going to be 90%, I bet. See that? 94%, 95%, like 94%. Okay, but if I do it from the beginning, if I run the code from the beginning, it sort of like reset everything. Reset all of the training. Okay. And then I'll just do, for example, 5 here. Okay, 5. So you can see like really the evolution of the accuracy of the training and the validation. So during the first epoch it should be low. Yeah, see that? This is only like below, it's been like really low, like 44%. Huh, interesting, interesting. I'll try it again, one more time. I promise one more time and we're done with this. Okay? I forgot, I want to set the epoch to 5. Say epoch to 5. Okay. Ta-da! First epoch, 50, 70%. Okay, yeah, 75%. It's low. But after that, the second epoch is it really jumps up by like 20 points, like 90 above. Okay, so the first epoch is always like low, but you have to kind of reset the whole thing. So I think when you just run this, it will just like my guess is because the error is already minimized. Even the last layer is already being pre is already trained, right? So you have to you that's why when you just repeating the second paragraph, you are not resetting the last layer, right? And the last layer has already like a pre-trained batch, sorry, pre-trained weights and biases, right? And those weights and biases are already like kind of good, like on the 90% or 95% or even 98%, um, right? So you cannot like uh, make it like really really go down. If you want to make it really good one, you have to reset it from zero, like from the beginning, and then you have to go to the first paragraph. This is what I was doing. So, okay, that's it. I hope this is helpful for you guys. Thanks for watching. I'll see you next time on the same channel. Bye.